quick question in the beginning. Is anyone here at CodeNode with a car? Because I might need a getaway driver after that talk. So if anyone could just come up. Anyway, so yeah, the title might seem a little bit controversial. And in fact, the talk is not going to be on what is bad in Haskell. It's going to be focused on what's good in Scala. And there may or may not be some ideas in the future which Haskell can borrow. And do we have any Lispers in here? Any people who program Lisp passionately and who can't stop telling people about how they like Lisp? So if you look at Lisp, you will probably be, if you're not familiar with Lisp, you will probably see all these parentheses all over the place, and you will think like, how can anyone possibly like this language? It's just completely odd. So this is what the Lisper sees, right? So utmost beauty, and this is what a non-Lisper sees, like all these parentheses, and it's kind of the same with Scala. If we talk about Haskellers, you'll say, well, this is just also, this kind of stupid syntax. It's so verbose, and it's kind of a lesser Haskell anyway. So Martin Odersky, the creator of Scala, actually acknowledged that fact and said, okay, so Scala is a gateway drug to Haskell, so we just rename Scala to Haskell later and just be done with it. So this is an actual slide. This is not photoshopped. Yeah. So the point I'm making is that to many Haskellers, Scala actually seems odd because you have this language which had some great ideas, but then it somehow got infested with this nasty JVM bug, which destroyed everything, and infested the syntax and infested the type system and things like that. And the point I'm going to make in this talk is that Scala is actually not a better Java, and it's also not a worse Haskell, although you can certainly program it that way. So you can actually use it like Java with syntax sugar and still continue to do your imperative programming and benefit from, I don't know, like lambdas, which Scala had before Java 8. And you can also write it like Haskell, so you can use almost the same concepts. JVM will obviously not always like that, but you could certainly do that. But what's nice about Scala is that it has its unique strengths and weaknesses. And those are very often overlooked. And they are actually often overlooked from both sides in the spectrum. And of course, I'm going to focus on the strengths here. And for a little bit of context, so I'm a PhD student in Munich, and what's kind of funny is that in the other track, there's a talk about how to build a theorem prover in Haskell, and our lab actually builds a theorem prover in standard ML. So this talk is not going to be that, but there's going to be some things about standard ML, because what many people don't know is that Scala has a very strong heritage from standard ML, and this actually gives rise to a couple of strengths in the Scala language. So to begin, let's talk about first-class citizens. And here's the Wikipedia definition of first-class citizens. Take a moment to read it. Right. So the gist of it is that you can have a thing is a first-class object if you can pass it around, if you can assign it a variable, you can manipulate it like all the other things in your language. And this section is going to be about how type classes and implicits are actually first class in Scala. So all of you know how type classes look like in Haskell. So you have a dedicated keyword called class, and then you have a name and a type, and you define just a list of operations. And in Scala, these type classes are being represented by traits. So how many of you know a little bit of Scala and know what the syntax trait means? Okay, so for all the others, think of it as a Java interface plus X, but we don't need this plus X right now. So you have a type parameter here, and you also give a list of abstract operations. So this is kind of the same. So there's no more boilerplate in Scala and Haskell. So this is really similar. So what do instances look like? Let's say we want to implement an ordering for lists. Then you say, okay, I can give an ordering for lists if I can give an ordering for A. And then I just defined it with pattern matching on the top level. So first thing to notice is Scala doesn't have top-level pattern matching. So this is already one source of boilerplate. So I've left it out here because the slide wouldn't be big enough. Anyway, so you would need to define this, you would need to implement this function and then perform a pattern matching and then basically the same. However, there's this weird keyword here called implicit. And actually what that does is that it marks this method to be picked up whenever something of its type is required. So when you have a function which requires an implicit ordering of something, then the compiler looks through all the implicit methods and implicit values which are there in scope, and then it will just, resolve everything and give it to you. And it's kind of the same if you think about type class and instances, how they end up in one of GHC intermediate languages. Because they're being compiled down to records, and also these records are being passed around. But in Haskell itself, at least not without extensions, you can't manipulate these records. So they are being filled out by the compiler implicitly. You can't actually get a hand on that. So you can imagine that as kind of explicit dictionary construction you're doing here. You explicitly construct these dictionaries and tell the compiler, this is one function how to construct these dictionaries. Here's actually an explicit dictionary. You can use that. Now, because these implicit instances in Scala are actually just values, so as you can see, you construct a value of this type class. You can have the full power of the language to manipulate these instances. So let's say we want to give a function which takes an ordering and flips around this ordering. So what you would do in Haskell is you would create a new type. You would create a new type wrapper, and then you say instance ord A implies instance ord whatever reversed A or something like that. So you have this additional type tag in there. You don't need to do that in Scala. So you can actually have a look at this trait, and you extend it with another function, and we call it flip or reverse or whatever. And this actually gives a near instance of the same type back. So now you can suddenly construct an ord of int, which is the actual ordering of int, like ascending, and then you call flip on it, and you get a descending order of ints. Now, many people criticize this feature because now you can basically create arbitrary instances for whatever, and you might have multiple instances of the same type around, right? So if you have an ordering of int, and then you call flip on it, you have another ordering of int, but they have differing behaviors. And in Haskell, you usually don't want to do that. Now, there are a couple of words to describe this. I've seen at least 3 of them. So some people call the type class coherence, some people call it confluence, some people call it uniqueness. And I like this term uniqueness best because it actually describes what it is without any technical terms. So instance uniqueness means that in any given program, for any given type class, a combination of type class and type, there's at most one instance. And Haskell or GHC tries to enforce that by telling you to not use orphan instances. In fact, this check is not completely safe. So there are situations, they are kind of contrived using orphans where you can violate this, and GHC won't notice. There's a blog post by Edward Young. So if you're interested in that, I think you can Google for just Haskell type class uniqueness or something like that. You will find it. And that's why some Haskellers say we don't want implicits like in Scala because it's completely uncontrolled. You can do whatever you want. You can violate uniqueness, and you won't even notice. You might get data corruption. Anyway, so what I'm going to argue is that contrary to popular belief, the implicit scope in Scala is actually very well defined. So you might need to have a look at the specification, but for most of the cases, you have to know very little rules. And you know the rules from Haskell, right? So where can you put an instance in Haskell, or where are you supposed to put an instance? You can put it in the module which defines the class, or in the module which defines the data type. And actually, you can do exactly the same thing in Scala. And in Scala, you don't put them just in the same module, but you put them in so-called companion objects. This is a technical term. Let's just say you can have a class and an object of the same name, and then they're somehow companions. So if you have a trait for ordering, you can have an object called ordering, and if you put instances there, they will be picked up by implicit search without importing anything. And this is exactly the same behavior you would get if you would adhere to Haskell's no orphan policy. It is exactly the same. And so some Scala libraries, they say, okay, you can have multiple instances if you want to. So for example, you want a monoid for the natural numbers or for integers. You can have either a monoid for addition or a monoid for multiplication. So in Haskell, you use new types, and the good thing about Haskell new types is that they're erased at runtime. We have kind of something like that in Scala as well, but it doesn't work so well. So sometimes you still get boxing. So people tend to avoid these new types. So they will just give you one monoid for addition, one monoid for multiplication. And what happens then is that they're usually non-implicit or not in the implicit scope. So you would need to import them explicitly, or have a piece of code which requires that you say import spire.implicits.int multiplicative, for example, and then it would give you the correct implicit. So some observations from real-life Scala libraries I've made. So these are sorted in increasing order of controversialness. So use companions as much as possible, which is the same as in Haskell. Don't use orphans. And the second thing is orphans are actually fine as long as they are hidden behind an import or not picked up implicitly. So you actually have to do something to get them, as opposed to in Haskell, where you import something and then you get all the instances. You have no way of opting out of importing instances. In Scala, you can actually do that. And this is a very well-known pattern. So if you have Spire, the library, it's a numeric stack, an algebraic stack for Scala, and it provides instances for stuff from the standard library. And also, there are also third-party libraries which provide Spire instances for other libraries. And what happens is that usually you have some sort of object which contains all the instances which are non-orphan, which are orphan or something like that, and you can import them. But by default, you won't get them. And yeah, the third thing is, as I've said, is avoid new types with an asterisk, because actually people in Scala do use new types, but in Scala they come with sometimes they come with a runtime cost, and I have to admit it's not trivial to figure out whether they come with whether a specific use type comes with a runtime cost or not. So that's actually something which Scala could learn from Haskell, proper new types. So now, I told you that these type class and implicits, they are actually first class, and this encoding of type class and instances as implicits, it has been known since at least 2010. There was a paper about this, and so these are first class, and since Scala is also object-oriented, we can now use object-oriented features with our type classes. So we can use all these fancy OOP features. So we can use overriding of methods to provide default superclasses. So how many of you have seen this default superclass proposal for Haskell? Not many. So in Haskell, you have a problem when you have a type class hierarchy, like functor applicative monad, and at some point later, you decide to insert a new class into that hierarchy, which happened with applicative functor and monad. All your code will break, because you have no way of saying, okay, I have a monad in my monad type class. If I have not already applicative super constraint, then here's how you could implement it automatically. Because every monad is also an applicative, but in Haskell you can't really say that in the class. So you would always, when you have a data type, you would need to implement functor, applicative, and monad, all three of them. There's no way to, like currently, to circumvent that. And in Scala you can, so you can just write trait monad extends applicative, and then you can give a definition of the applicative operator in terms of the bind operator. So if at some point your Scala library decides to add another superclass to your class, they will just provide a default implementation and your code won't break. You will still have to recompile, because it's usually not binary compatible, but it's at least source compatible. Yeah, then you can use mixins to get minimal complete definitions. So there are a couple of type classes which have, like, I don't know, a bunch of methods, 5 or 6, and you can use 2 of them to implement the others. And you maybe have 3 sets of those. So you can use A and B to implement C and D, or you can use C and D to implement A and B, something like that. And what happens in Haskell is that you just put that into the header documentation. It's got special support for that. I don't know since when, but it's got that support. And in Scala, what you can do is you can just give a different trait. So you can say trait ord from something, and then you can have another trait ord from something else, and you can mix it into your object, and it will just work. And the compiler will check that all the definitions you want are actually defined, and that you don't have something circular, or at least, well, you can still produce something circular, but it will be much harder than in Haskell. And also, you can use factories to get default signatures. So if you have a class which can be automatically derived by generics, then very often you put something in these classes which implement certain functions if there is a generic instance in scope. And this requires a Haskell extension. It's actually, I think it's called default signatures. And in Scala, you can just use regular functions to do that. So you can just use the factory pattern. It looks like we're using design patterns, so I'm just going to stop here. There would be a couple of more, but I'm not going to let Clippy pull out the Gang of Four book. Okay, so there's that. Let's switch to standard ML. So standard ML is the best functional language which nobody ever knows outside of the theorem proving domain. So it's been developed by this guy, Milner, in the 1970s and 80s. Of course, he had some help. But yeah, the main application domain is actually theorem proving. So I'm not sure if there are any significant standard ML projects which are not theorem provers. Anyone know anything? Probably not. So for the time, on 1970s, 1980s, were already quite advanced. It got type inference, garbage collection, all these things, and some people say, well, it's been stuck in that age because the standard ML, the standard, is not evolving very quickly. So it's essentially, let's say, fossilized. So there are sometimes, so there have been updates to the standard, but essentially the language is largely the same. It stays largely the same, which also means that a lot of old code is still compatible. Just imagine if you had like GHC 6.12 code lying around, which would still compile with GHC 8.0. This is standard ML. So you can take code which is 10 years old and still compile. So what is interesting about ML is that it has this module system, which some of you might know from OCaml. So a module is just a named collection of values and types, and those may be abstract. So you can think of it as just some sort of interface where you can put function, headers, and types. And the functor in ML terminology, so please forget what functor means in Haskell, because there's no way, it's not related at all. So it's essentially a thing which maps an input module to an output module. I have an example for you. So let's say you want to implement trees in standard ML, or tables, you know. So you give a signature of called key, and this contains a type key, which means this is the thing you map from in your map. And then you still have to give an ordering. So this is kind of complete. It's similar like an ordering type class. And now you say, okay, I want to define a map, which usually is called table in ML terminology, and you have a couple of operations like empty and insert, and this looks like the data.map module essentially. So you have a type for maps, and then a couple of operations in them. But what already strikes as odd here is that the maps, they don't actually have two type parameters. They just have one type parameter, which is for the value. The key type is in here. So you can't just change the key type if you have a value of a table, right? So this is fixed. So now we just need to implement this in some way. So this is just a signature. There's no implementation yet. So how can we do that? Now we can use functors to do that. And the functor, I said, is a thing which maps one module to another module. In that case, it takes a module which has the signature key, so something which implements the signature, and it gives back something which implements that signature. Right? Here so far? And we can now give an implementation, and we say, okay, we can implement this with some tree, or here I just said something with a list, so you can just pick anything what you want. And what's interesting now is that you can actually give multiple implementations. So you can have a functor which produces trees, which produces maps backed by lists. You can have a functor which produces maps backed by 2, 3, 4 trees, or whatever, or by red, black trees, or whatever you want. And all these are completely the same. So you get exactly the same. You get exactly the same signature in the end. You can use all these operations uniformly. And what's even more important, you can always swap out the implementation, and the compiler guarantees you that it's safe, because you have always ever programmed against the interface and not against the implementation. And I can compare that to Haskell when you have modules which have a lazy and a strict variant, and you can swap out the implementation, and the compiler doesn't actually check that that these two modules have actually the same signature. So you have to kind of make that sure by hand. And in ML, you would just give a signature, and then the compiler would check that both these implementations, although they're slightly different, actually implement the same interface. Okay, so how can we use that? So we can just give an implementation of this key signature for integers. So we can say the key is type int, and then the ordering is some ordering function. And then we can invoke this like a function, essentially. We say, give me a table for this int key, and then we can use this int tab prefix to access all these operations. Now, this is fairly simple, but there are going to be problems. So have a look at this code. So we create two structures which have the same initialization. So you call this table functor on 2 times the same structure. Now the question is the two table types you get there. So this int tab1.table and this int tab2.table, are they actually equivalent? So who says yes? Who says no? So why no? Exactly. So the answer is types are generative in standard ML. So what does that actually mean? It means that whenever you invoke this, you create a fresh copy. So you can actually think of that as a time side effecting thing, because it gives you a new table type, and those are not compatible. And there's a distinction between that. Those are called generative functors because you have a functor, and when you apply them, it generates fresh types. And OCaml, on the other hand, it has applicative functors, not to confuse with Haskell's applicative functors. They are actually what a Haskell would probably expect. So in OCaml, these two would actually be compatible, I think. I hope I'm not. But anyway, so OCaml has recently, I think, also gained the possibility to use generative functors. And in standard ML, there are a couple of implementations which do something like that. They try to extend this module system. But in some cases, it turns out to be unsound. For example, if you have higher order functors and stuff like that. So the baseline in ML is you have functors, just first order functors, and they are all generative. So that's kind of the bottom line you can take away. And now why I'm telling you about standard ML, right? Because in Scala, it's actually exactly the same. So this is where Scala's ML heritage shows, I think. I'm not sure whether it was intended. You would need to ask Martin Ojarski about that. But this is actually what happens in Scala. So you can implement exactly the same thing here in Scala. So you can give the signatures here, and you can see not only do traits serve as an encoding for type classes, they also serve as an encoding for ML signatures. So they're really versatile. And then you can do the same thing. You can create two instances of this module. For example, here you could say, give me a module which uses this implicit integer, and then you could use something which uses the flipped integer. And now this operation only compiles if T1 and T2 belong to int tables. So if you would stick something in here which came from int tables ref, it would not compile. Compiler would complain, those are actually two different types. Don't do that. And why this is actually quite relevant to what I told you earlier about this instance uniqueness, because if you have this, uniqueness is not a requirement. So you can program safely without uniqueness. Why is that? If you create such a module, and then you have two different sets of this type, the compiler guarantees you that when you perform this union operation, which is usually some sort of hedge union, which is very efficient, and these operations, they have the assumption that both the orderings are exactly the same. So if you don't have uniqueness, you could have different orderings, and the result would be broken. But with this, the compiler will actually check that both tables belong to the same structure, and they must have the same ordering operation. And now you can completely, you don't actually need to deal with uniqueness or anything like that. So this is really nice. Of course, it has its downsides, because if you want to link two modules together, third party, let's say, and they happen to use the same ordering for something, the compiler won't check that, right? So it won't know that, and it will refuse to compile, although you know that it's the same. So you would need to do manual conversion something like that. But I think it's a small price to pay, because if the collections library were actually designed that way, and there's for those of you who don't follow the Scala ecosystem, there's currently running a call for proposals of how to redesign the Scala collection library. There's a existing implementation for that by Bill Venners, used in Scala test, and I think it's really elegant, because it kind of combines the strength of type classes and modularity together. All right, so questions up until this point? Well, then let's move on to the next lesson. And the next lesson is going to be about generic programming. Who of you have been to the previous talk? There might have been some generic programming involved there. So what is generic programming? So first of all, let's define what polymorphism is, or parametric polymorphism. And this is abstracting over types. This is easy. Like Scala has it, Haskell has it. We all know how that works. Generic programming adds something on top of that. It's not just abstracting over types. It's abstracting over data types. So you have data definitions with the data keyword in Haskell, and then you can kind of abstract over its structure. You can take two different data types and see their structures in a similar way. And generic programming has a lot of use cases. So I think the initial use case for Haskell came from the series of papers called Scrap Your Boilerplate. And then there's, in Haskell lens, there's stuff for automatic lenses, how to produce lenses automatically. There's a library for parsing and pretty printing. And of course, the most general thing you can do is, given a data type and a type class, give me an instance, give me an implementation of this type class for this data type for free without me having to write down boilerplate, essentially. And this is also quite pervasive in Haskell. So there are a couple of libraries which deal with that, and GHC has built-in support. If you put some derived generic in your as an extension, you can use that. And then there's a couple of libraries on top of that which make it slightly nicer to use. So let's have a look at an example. So let's say you define this data type in your code. So you have a just standard list. And now you want to derive equality for that. And now let's just assume that the Haskell compiler does not have that built in. Like, let's just assume EQ is your copy of equality, and you want to implement it yourself in the library using generic programming. So how would it proceed? So you would need to come up with an implementation of equality. And so what happens is that you write down these, or you meta-program these equations, right? So you say, if I see two instances of the same constructor, they are going to be equal if and only if all their components are equal. And then you have some more equations which say that if you have two different constructors, they are not equal. But let's ignore them first. So, of course, for nil, it's easy. Nil equals nil is obviously true. And if you have two const cells, then x needs to be equal to y. And now, what's the rest here? So now xs needs to be equal to ys. And can anyone see the problem here? So we're trying to figure out the instance for equality for list of A. And during that, what do we need? Right, the same instance we're actually deriving. So we now need to use this instance somehow recursively. We're trying to derive it, but at the same time, we need it. So that's kind of a dilemma. Now Haskell is lazy, but it's not something, like this scenario is not something the compiler, the GHC, has supported all the time. It has been introduced. This is a screen cap from one of the Scrap Your Boilerplate papers, and please take a second to read it. Right, so the precise algorithm actually doesn't matter, but the bottom line is you have a cyclic situation, so you want something for list of A, and while doing that, you need it as well. So you have a cycle in your constraint resolution, and what GHC does now, it tracks what it's currently trying to solve. And in this pipeline, if it sees something which is exactly the same, it will just shortcut. Right? So this is essentially, I wouldn't necessarily call it a hack, but it's a special case in the type checker which has been introduced to support that kind of situation. So essentially what I'm saying is that in Haskell you need compiler support for that kind of thing. Now, in Scala you can actually implement that as a library. And Sabin isn't here, but there's going to be Shapeless. And Shapeless is the generic programming library of Sabin, which incidentally has started as, I don't know whether it was a practical joke or something, so someone said, like, how about we implement, or how about I implement Scrap Your Boilerplate in Scala? And then this experiment kind of got out of control, and you have version 2.2.5 and something like that. and people actually use it in anger, And recently, so Shapeless has had generic programming support for quite some time, and recently it gained support for this thing called lazy. So lazy is a type constructor, which, as the name already says, contains a lazy value. But not only that, if the compiler is currently doing implicit resolution of a thing, and you wrap it into lazy, it will actually perform the same check as GHC does at this point. The only difference is that this is implemented as a library. So this is completely user code. To be completely fair here, this is user macro code. So it's code which runs inside the compiler, but the Scala compiler actually has some sort of well-defined API, let's say sort of well-defined API exposed to the user, which is kept stable across versions. And there's also a completely new version coming up, which also supports alternative Scala compilers. Anyway, so this is macro code, which essentially does the same thing, and you could just clone that code in your own project and adapt it to your needs. There's no need to actually modify or patch the compiler to do what you want. You can just modify the Scala code. And I'm going to show you a quick demo so that you know that I'm not lying to you, because this code actually works. So let's have a look. So we have sets.scala, no, lazy.scala. So here's this standard list I'm defining, which has a cons and a nil case. This is another thing which Scala could learn from Haskell, data type definitions with less boilerplate, because to be fair, you can't really get shorter than what you have in Haskell, and at least for the general case. And this is just annoying in Scala, to be fair. Anyway, so you have a type class for showing values, for converting to strings, and then you have some base instances. So you have an instance which shows an int, and then you have an instance which shows a nil. And here's another thing, which some people may or may not notice. Scala has built-in data kinds, so we don't need this compiler extension. We have it already, right? It's just because of OOP it's there. Anyway, I digress. So here's this definition, this implicit for showing a const cell, and then here's the other implicit for showing a list itself. And you can see that if you look at it, there's this cycle looming. So you have the show list requires a show const, and the show const requires a show of list. So the compiler will most likely yell at you, but not if you actually use this. So I can just go here, say clean, compile. So this will compile fine. Now, the negative test is if I remove that, what happens is the following. Let's just uncomment this. And essentially what I'm doing is I have a second copy here which doesn't use lazy, which just uses the raw types essentially. And now I compile it. And now the compiler will complain that there's a diverging implicit expansion. So it will actually detect that there's a cycle and will just abort, because the Scala compiler doesn't know what to do with that. It doesn't do lazy implicits essentially. So this lazy type, what it gives you is essentially full control over lazy instance resolution, and it's all implemented in library. And I think that's actually a quite nice achievement. Now, to show you that it actually also works at runtime, so that it's not just smoke and mirrors, it compiles ship it. Oops. So I'm just going to recover the original code. And there's some test code below, which will construct the list and then show it, and we'll just check if the result is as expected, whether it terminates. So if I say now run, compiles, and it will actually give the correct result. So I think that's quite a nice achievement, that you can build all these things in library. And yeah, as I said, this requires the use of Scala macros, and macros are meta-programming, and obviously many ecosystems have it, even Haskell. So even with Haskell's expressive type system, you sometimes need meta-programming, and I've already given some examples for using generic programming, and these are some examples which also use template Haskell. So Lens uses template Haskell, Yesod uses template Haskell, and invertible syntax. And as you can see, the use cases for template Haskell are kind of the same as use cases for generic programming. So I think people in Haskell community, correct me if I'm wrong, are trying to move away from template Haskell, try to do as much with generic programming as possible. So let's have a look. So there could be many talks which compare template Haskell and Scala macros because they kind of satisfy the same purpose, or they have similar use cases, and there could be papers and books about this distinction or a comparison. But just here's the bottom line. So in Scala, macros look just like regular functions. And you just write def, and then you give the name of the macro, and then give arguments, and then an equal sign, and you just have macro something. And this is the only indication that there's a macro going on. If the user calls f.whatever, and this whatever is a macro, the user won't actually notice it. It will just look like a regular function call. On the other hand, macros in Scala have full power, so they may access networks, they may access file system, and anything more of that. And they're actually like proof of concept libraries which exercise that. So at some point in Scala, there was a thing called type macro. So a macro could not just produce expression trees, it also could produce top-level type definitions. I think some people have decided that it's a bad idea, it doesn't work right, so people don't use that anymore. Anyway, there are some somewhat less dangerous versions of macros which do the same thing or achieve the same effect. And so what you can do is, for example, if you want to write a program which communicates with a data type, you need to define your schema in your file, in your Scala file. So some people they invent some sort of XML or JSON format for their schema, and then they use code generation to produce the SQL schema, and then they use another code generator to produce the Scala files. But what you can actually do with Scala macros is you can, during compilation, you can connect to your database, read out the schema, and then produce the types in Scala. I think we all agree that this is somewhat dangerous because now your build system depends on the availability of your database service during compile time, not just during test time. So not many people do that, but in theory you could do that. Yeah, and they are transparent. So as I said, they calls. Yeah, question. So the question is, can you define, for example, new variable bindings for Scala macros? So what happens is that I haven't put that here. Actually, I now realized I forgot it. So when you call a Scala macro, it all needs to be Scala syntax. So you can't just invent arbitrary syntax in there. Especially you can't produce new kind of binding constructs which you want to. So you can't just redefine pattern matching if you want. No, not at all. On the other hand, at Scala World this year, a master student at EPFL showed a demo of parser macros. So there are now parser macros, and there you can make up whatever you want. And the audience wasn't very clear if it's genius or evil, maybe both. But I'm going to wait for a Lisp macro in Scala now. So a parser macro which takes Lisp and converts it to a Scala tree. Yeah. So they're transparent, so the calls look like regular function calls, and they're irrelevant with compiler. You don't want to know how the compiler does it because it involves advanced JVM class loading hackery to make that work. But there's a really nice example, what I mean with transparent macros. So I told you about this type class encoding in Scala, and what I didn't tell you is that like operator syntax in Scala doesn't come for free. So if you have an EQ type class in Haskell, which defines the operator equals, you can just write in your code A equals B, and then it's just going to work. You can't do that in Scala. Now, why is that? Because operators are translated to function calls. So equals would need to be a regular function on the object A. And since these type classes are separate from the types of these objects, there's no equal operation. So you can't just call it. Now, what Scala libraries usually do that, you can actually define implicit conversions. So you can have another class which wraps an A and adds these equality operations, and which delegate to the type class instance. Initially, this was called pimp your library pattern. There's actually, I think that appears in some paper, I think. Now it's usually called syntax enrichment. So you can just take some arbitrary value and you can just enrich it with new syntax in your library. And if you hear that from me telling you that you have this wrapper which delegates, you probably think this is going to be brutally inefficient. And it is. So here's where macros can help. So this is also an example from Spire. But actually, Spire had a special case for that, and now it's been pulled out into separate libraries, so you can do that for your own Scala library if you want to. So if you write this triple equals because, I don't know, double equals is already hard-coded into the compiler, and we want to look more like PHP or something like that. So we use this triple equality and say, okay, so if A is equal to B, then do this or do else do that. And what happens after all these implicit conversions, all this wrapping, all this delegating has kicked in is this. And you can already see this looks kind of horrible, right? So you have this EQ ops, which is this wraparound A, and then you put the instance here, and then you call this function, and then it's like 3 layers deep. There's the actual operation, and then up there's the high-level thing you wanted to express. Now this step is done with the vanilla Scala compilers. No macros involved. It's just regular implicit machinery using implicit values and implicit conversions. Now this step here, this step below, it's done by a macro, and it's actually hooked into the type class type classes, and maps kind of inlines these calls. It kind of inlines these calls. It does something more, so it also provides a mapping that these triple equals is being rewritten to this EQV and something like that. And there's a library called Simulacrum, and there's another library called Machinist. And Simulacrum provides an annotation called addTypeClass. So if you just write create order and something and just slap addTypeClass on top of it, it will do many of these things automatically for you, and it really reduces the amount of boilerplate you have to write. So anyway, so the point here is not that Haskell can learn this boilerplate from Scala, but maybe Haskell can learn some boilerplate avoiding techniques from Scala, because we really have a lot of pressure to avoid boilerplate, right? So we kind of go crazy and invent all these things. Okay, so final lesson for today is the ecosystem. And we've heard a talk about Shake, about the build system, but really the most common build system in Haskell is Cabal, and the most common build system in Scala is SBT. So now there's the question, what is actually better? So what is which tool can learn from the other one? So I made a highly scientific study. I Googled for Cabal Hell and SBT Hell, and Cabal Hell gave more than 600K results, and SBT Hell only 400K, so clearly SBT is the better build tool. So Cabal just do whatever SBT. Okay, so of course I'm joking. This is not what I'm talking about when I talk about ecosystem. Now the library ecosystems for Haskell and for Scala, they are huge. And in Scala, they are even more huge because there's the whole JVM ecosystem behind it as well. So I'm just going to pick one example where I found that the Scala ecosystem is better than the Haskell ecosystem. I hope you you will excuse that kind of nitpicking from me. And this topic is law checking. So, as I've said multiple times, type classes are used pervasively in Scala and Haskell. They're common point of their center of library design in both languages. And most of these type classes we define, they actually come equipped with laws. At some point, I think in Scala we had a library which extended another library with some type class which didn't have laws, and we called them outlaws, like lawless type class, something like that. And anyway, so many of these classes, they have a rather complicated system of laws because they extend from other classes, right? So this is a picture from Type Classopedia. I suppose you are familiar with that. You have seen it at some point. Anyway, the details are not very important, so you just see there's a lot of arrows going on. And all of these arrows somehow denote that there's implementation inheritance, there's structure inheritance, there's law inheritance. So there's a lot of different things going on. And here's another example from the Spire library. So you have, you probably can't read it, but this is a field. It's an algebraic field. And then a field is an Euclidean ring, and it's also something I can't read. And this is a commutative ring and a rig and whatever. So it all goes down to some semigroup at the bottom. So all of these things, like every layer in there, it adds one more law or a couple of more laws. So it's really important to get this straight. If you implement a Euclidean ring for some type, you want to be sure that actually, the laws are all satisfied. And the management of these laws becomes very important. And not just checking that all the laws are implemented, but also to make it efficiently. Because, in the Euclidean ring is a semigroup in multiple different ways. So you inherit a semigroup from the additive variant, from the multiplicative variant, and a Euclidean ring is a ring and a rig, and those rings and rigs, they are also semigroups in different ways. So if you do it naively, then you will end up with tons of duplicate law checks. And there's a library called in Scala called Discipline. There's also another library which is called, I forgot it. Anyway, so there are a couple of libraries in Scala which attempt to solve this problem. So if you run the test case of Spire, you will actually see this. So you have, this is the type, and this is the root type class, Euclidean ring. And then you see all these inheritance things. And there's a difference between what a colon means and what a full stop means, what a colon means. Anyway, so the takeaway message here is that this library actually makes sure that all laws are checked exactly once. And I tried to find something like that for Haskell, and I found a couple of libraries which support, law checking for monoids or for kind of simple things, but none of them I've seen they actually tackle this problem. And I think this is going to be very important. For example, Spire, it does numeric programming, algebraic abstractions, and especially for those types, it's really important that you check all the laws, that you make sure that everything is satisfied. Yeah. Yes. So this is checked by the Scala version of QuickCheck, which is called Scala check. But anyway, it's the same thing. Yeah. Okay. So that was the final lesson. I hope you've learned something. Questions? No questions? Well, then, one question.
Something else that one could look up at the top. Was that like the main point of Scala? Good. That's a beauty.
Say that again, please. So you're asking for further reading? Yes. Okay, so further reading. Go learn standard ML. Then you will understand a lot of Scala. Read Scala, the good parts. It's actually called functional programming in Scala, but it's kind of the same thing. We still need a book called Scala, the ML parts. So what else? Yeah, go read up on macros. I think they are kind of powerful and dangerous tool, but employed efficiently, then I think it's really nice. And then have a look at the cats library in Scala, because the cats library actually employs some of these techniques like law checking pervasively, and also the simulacrum, what I mentioned, that you can just slap an annotation some type classes. And I think actually with these libraries we do type classes better than in Haskell. And also you can have a look at the Scala test library for these collection libraries, alternative collection library, which doesn't require instance uniqueness. So these are the main points from my talk. There are a couple of more. So if you really want to invest some time, go have a look at Shapeless. If Mal7 were here, the focus of the talk would have been slightly different, more stuff of Shapeless, so singleton types, more trickery with implicit, something like that. Yeah. There's also a talk by Edwin Brady and Mal7 from Strangeloop, where they both try to implement effects. And it kind of worked in Scala, but it's not something I would recommend to use, but it's very enlightening to see how this kind of thing can be encoded in Scala. Okay, yeah, that's